Fine. I hope you understand the procedure. The previous slides included a lot, equations, but it is just for we got the final equation in here. That is sediment equals to this. But this is only happen to when you give a pressure. The initial pressure is in this part, and the final pressure is in this part. That you only use CC, right? But let's say if the initial sigma naught dash is in here, and finally after you give additional delta sigma dash, and the final stress is located in here, so it cross what? It cross actually the pre-consolidation pressure. You can't only use CC, consider this part, the slope of this part, right? So the pressure actually crossed the pre-consolidation pressure. Under this situation, we need to consider both CS and CC. That is the flatter part and the steep part. So in here, let's say, in an over-consolidated clay, that is the initial position of the soil is in here. The state of the soil is in here. It is an over-consolidated soil, right? After you give additional load, maybe it locates in here. It is a normally consolidated soil, right? So let's see. If this happens, how to calculate the sediment? So in over-consolidated clay, let's say that delta sigma naught plus delta sigma dash smaller than delta sigma c dash. So that, let's say this is let's say this is sigma c dash. That is pre-consolidation pressure, okay? Pre-consolidation pressure. So if the initial pressure is in here, after you give additional pressure, it is located here. It is both this stress level is smaller than sigma c dash. That is, soil is still an over-consolidated soil. So delta E equals to this, right? So you need to change CC to CS because now the slope is not CC. The slope is CS. Understand? And it said CS is slope of rebound curve. That is swelling curve and is defined as a swelling index. So actually SC, the sediment is small, right, in this part, right, because it is elastically. We know that under this part, in the over-consolidated soil, the compression is small. The curve also is flat. And CS in here, it is the same with previous one, but in here we just change the CC to CS, right? Because soil is in this part. We know that soil, if both the stress is in this part, we use CC, and both stress in this part, we use CS. But what happened if the initial state of the soil is in here, after you give additional load, the soil state is in here. That is, initial state, soil is pre-consolidated. The final state, soil is normally consolidated. So under this situation, if this happens, sigma naught dash plus delta sigma dash higher than delta sigma c dash, that is, initially in here, after additional load, it is in here, higher than the pre-consolidation pressure, right? So under this situation, SC equals to this. That is from the initial stress to pre-consolidation stress in here. Initial to pre-consolidation stress, we use CS, right? And from pre-consolidation pressure to here, we use CC, right? So actually, pre-consolidation pressure separates the consolidation into two parts. One is a flatter part, another is steeper part, or one is in the swelling, in the overconsolidated part, another in the normally consolidated part. So actually, you see in here, we have a sigma node dash. Sigma node dash. Because we use sigma node dash separated into two parts. One is elastically, another is plastically CS and CC. Understand? So this is the different equation, different calculation when you find the additional load locates on the two sides of the preconsolidation pressure. Okay. So this is how we use primary consolidation test to calculate the settlement. Actually, if we want to get this, you just need to compare the load, right? Compare the load. Do the comparison. Compare the load first, right? If it is in this part, then you use this. That is this equation. If it is in this part, you need to use this equation. But before this, you need to conduct a laboratory test, right? To get CS and CC, right? And to determine the preconsolidation pressure. This is the first step. And then you can use the additional load you want to apply to calculate how much settlement happened to the soil. Understand? This is just the primary consolidation. We said that a whole consolidation process have two stages. Let's go back to here. Have three stages. That is, the first is initial pressure. Initial compression actually is small, and then primary consolidation as pore water is expelled. This is the primary consolidation. All the consolidation we explained, laboratory test, the spring cylinder models is all for the primary consolidation, because we say that primary consolidation is a transfer between pore water pressure and effective stress, right? So this is primary consolidation. And then there is a second stage, a third stage, that is secondary consolidation. As soil fabric, we adjust plastically. That is after pore water pressure expelled, all the stress transferred to the solids of the soil. Soil still happens some settlement. Those settlement called secondary consolidation settlement. So that is because, in particular, it happened to softer soil, right? This is caused by readjust of soil microstructure. Maybe the orientation of the particle under the constant load changed, or maybe particle breakage, or maybe something else happens to the microstructure. But the pore water pressure keeps zero in this part, that is secondary consolidation. Actually, in granular material or in stiff soil, secondary consolidation is small. But for softer soil, secondary consolidation settlement is actually cannot be ignored, cannot be neglectable. So it is also important to calculate secondary consolidation settlement. Let's see what is secondary consolidation. The secondary consolidation is observed after the excess pore water pressure is completely dissipated. Secondary consolidation index, we use C alpha, is used to describe secondary consolidation It can be estimated from plot of void ratio against log of time, which is usually a linear relationship. So what is, we have another parameter C alpha in here. So what is C alpha? How we obtain C alpha? We can, this is log maxima dash. We have first point, second point, third, fourth, finally. We have such a curve, right? Understand? We have such a curve from one-dimension test. But for each point, we say that for a one-dimension consolidation test, each loading step lasts at least 24 hours, right? In the standard, it asks for 24 hours. 24 hours, okay? So during the 24 hours, you always observe the height change, right? That is actually the void ratio change, right? So actually, you can obtain the void ratio and time relationship for first, second, finally, maybe each stage, each loading step, right? For the first one, you can go to void ratio change with time, right? Because it lasts for 24 hours. We always obtain with computer the void ratio change or the segment, the height change, right? You can calculate it. And for the second stage, third stage, fourth, fifth, each stage, each loading stage lasts for 24 hours. So you always know that for each stage, you can always obtain a void ratio time relationship like this. If you plot on this plan, it will look like S shape. S shape. So an inverse S shape actually. So it looks like this. In here, actually, this is the pre-compression, the stage one. We just preview the figure, right? This is the first stage, stage one. And in here, the second stage, from here to here, this is actually primary consolidation. That is the consolidation we studied previously, right? And the secondary stage is start from here. How we determine the second stage? So we have an S shape, right? If you draw the tangent in here, another tangent in here, the cross point gives you the start time t of the second consolidation. So from here, it starts the second consolidation. The first consolidation, we think it is finished, and the corresponding void ratio in here is void ratio for second consolidation. So void ratio decrease again from this point, right? So pre-compression, primary consolidation, secondary consolidation, right? And the slope, we define C alpha, is this slope. Is this slope. How we calculate the slope? Again, you always have time, right? You record the time, you record the compression of the soil, that is, you record the void ratio change with time. So you can got 2 points on this tangent, right? And then with 2 points or 3 points, you can always calculate the slope. This is mathematics. Okay, so after you got C alpha, again, C alpha equals to this, you see, actually it is the delta E in here. For example, use these 2 points. Delta E in here, right? This is a delta E, and this is delta log T, right? This. So in here, C alpha is secondary compression index. Delta E is change of void ratio from T1 to T2, right? T1, T2 is time. It's time at different time, right? The magnitude of the secondary consolidation can be calculated with this. directly give you the equation in here. And it gives you another way to estimate C alpha. That is C alpha dash equals to this. It doesn't matter, it is just how to say, correction of C alpha. It doesn't matter. You can use C alpha directly in here, or C alpha dash, it doesn't matter. We usually directly use C alpha, not C alpha dash. Okay? So this is a secondary consolidation index and a secondary compression settlement. Okay, so we got actually, if it is a softer ground, you need to calculate primary consolidation and then secondary consolidation and plus these two together, then got the final settlement. It is the same with previous slides in here. So we're going to go into it. So this, up to here, we actually finished the main part of consolidation of soil in here. So in this chapter, because now it is online teaching, so I want to give you homework in this chapter, but we do have a question in this chapter on the examination. Okay, do you remember the practice we did in last class? Yes, it is almost the same with the practice. Because you see in here, if you want to calculate the settlement, you need to know what? You need to first got CS and CC, right? You need to understand how to determine the pre-consolidation pressure. So that is all of those data, all of those parameters based on the void ratio pressure plot, right? So how to got the void ratio pressure plot, it is important. Okay, we stopped here. Finished this chapter. In the next two class, I give you tutorial. We want to go to shear strength of soil. Let's talk about shear strength in next semester because it is more about foundation soil, about slope, stability of slope. So we can talk about in foundation engineering. From next class, I will go from the first chapter, give you tutorial on those main practice. Fine. And I think that you can start review your textbook, review those videos, and try to do more practice.